In this video, we are going to study carbonyl compounds and their reactions. Precisely, we are going to cover introduction to carbonyl compounds. We will also tackle properties of carbonyl compounds such as aldehydes and the ketones. And lastly, we will discuss some examples of carbonyl compounds. We'll be giving displayed and structural formulae of aldehydes and ketones. Before continuing with our topic today, please like this video and subscribe to our channel. Do not forget to hit the notification bell for updated videos. What do you understand by carbonyl compounds? What are carbonyl compounds? As you know, carbonyl compounds are compounds that contain the carbon double bond oxygen or carbon oxygen double bond group. This group you find here is the carbonyl group. In this carbonyl group, a carbon atom is double bonded to an oxygen atom, and this is a polar molecule. This group is a polar as a result of the difference in the electronegativity between oxygen and the carbon. It should be recalled that in carbonyl group, the functional group is found in compounds such as aldehydes. It is also found in compounds such as ketones and compounds such as carboxylic acids. With aldehydes, in aldehydes, you will see that the carbonyl group has at least one hydrogen attached to it. It has at least one hydrogen attached to it. One hydrogen attached to it. In this is it here. We will have a hydrogen attached to it. That is for aldehydes. And the carbonyl group is at the end of the carbon chain. Always notice that in aldehydes, the carbonyl group is at the end of the carbon chain. But in ketones, the carbonyl group is in the middle of the carbon chain. This is it. That is another one. That is the ketone. So as I said, the carbonyl group, which is the carbon oxygen double bond, is an organic functional group found in compounds such as aldehydes, ketones, and carboxylic acids. I said that in this group, the carbon atom is double bonded to an oxygen atom. In this group, the carbon atom is double bonded to the oxygen atom. So the carbon double bond oxygen, that is the group. It is found in aldehydes, it is found in ketones, and it is also found in carboxylic acids. So now, for the properties of this group, you will notice that properties of aldehydes and ketones. You will notice that the carbonyl group is polar, as I said. The carbonyl group is polar. This is it here. The carbonyl group is polar, with carbon having a partial positive charge and oxygen a partial negative charge. This is as a result of the difference in the electronegativity. So now, the polarity in the carbon-oxygen bond will influence the properties of aldehydes and ketones. It will influence the properties of aldehydes and ketones. And one of the properties that is easily influenced by this polarity in this bond is their solubility in water. Their solubility in water. You should notice that this bond, let me write it again for you to better understand. We have carbon here. Let's just put it like this in this one. There's another carbon here. Let me say there's another carbon here. And we have a molecule of water here. Here we have a lone pair of electrons on the oxygen. What happened here is that there is there is a hydrogen bond that is formed here. the polarity of partial positive on this other side. So if you look at this critically, you will see that this is the polarity. This is what can the polarity of the carbon-oxygen bond in the carbonyl compound can cause. Regarding their solubility in water, for this reason, aldehydes and the ketones of small molecular mass are soluble in water. Aldehydes and the ketone of very small molecular mass are very soluble in water because they can form hydrogen bonds between the lone pair of electron on the oxygen of the carbonyl group and the hydrogen of the water molecule. This is the hydrogen bond here. Hydrogen bonding. Formation of hydrogen bonding between water molecule, between the water molecule and ketones and aldehydes. So generally, because of the polarity of the carbonyl group, ketones and aldehydes are very soluble in water. They are very soluble in water because of their polarity and because they can form intermolecular hydrogen bonds with water molecule. But it should be noted that as the size of the ketone and the aldehyde increases, as the size of the ketone and the aldehyde increases, what happens? The solubility decreases. The solubility decreases due to interference in hydrogen bonding by the hydrocarbon tails of the aldehydes and the ketones. Another reason is that as the number of the number of carbon atoms are also increasing, van der Waals forces predominate between the molecules of aldehydes and ketones. So that is the reason that as the molecular mass of aldehydes and the ketones are increasing, what happens? Van der Waals forces predominate. As we discussed in our in our previous video, alkyl groups are electron donating. Alkyl groups are electron donating. You will notice that alkyl groups are electron donating. For instance, I want to give an example of an aldehyde. This is an aldehyde here. We have an aldehyde here. Here is a propanol. And we have another one here. This is propanol. Okay, these are ketones. This is a ketone. This is a ketone, and this is an aldehyde. This is an aldehyde. All of them have the same molecular mass. All of them have the same molecular mass. We expect their boiling point. We expect their boiling point to be the same, but that is not the case. This is propanol, and this is propanone. All of them have the same molecular mass, and the molecular formula is C3H6O. All of them have the same molecular formula, different structural formula. They are all isomers. Propanol is an isomer of propanone, and propanone is also an isomer of propanol. We expect these two compounds to have the same boiling point and the same melting point. But that is not the case. As we said, alkyl groups are electron donating. So here, you will realize that the ketone has two alkyl groups there, donating electron on the central carbon. Here we have just one alkyl group, which is the ethyl group, which is donating electron on the carbon. Here we have two methyl groups that are donating. It should be noted that most of the electrons donated by the alkyl groups to the carbonyl compound are grabbed by the electronegative oxygen. Most electrons that are donated on this carbon here, that are donated to the carbonyl carbon, electrons donated to the carbonyl carbon here are taken over by the electronegative oxygen. So all electrons that are being donated by the ethyl group here go directly back to oxygen. Oxygen is more electronegative than the carbon. Electrons that are being donated from the two methyl groups on the ketone to the carbon are taken over by the oxygen there, because oxygen is more electronegative than the carbon. For this reason, you will see that the oxygen atom in a ketone, the oxygen atom in this ketone here has more negative charges than the oxygen atom in the aldehyde. I said more electrons are donated here in the ketone than in the aldehyde, making the ketone more stable than the aldehyde. And it should be recalled that the electron donated to the carbon of the carbonyl group here in the ketone are taken or are drawn or are grabbed by the oxygen there. The same way, electron donated on the carbon in the aldehyde here are taken by the oxygen here. For that reason, this makes the carbon-oxygen bond in the ketone more polar than the one in the aldehyde. The oxygen atom, once more, the oxygen atom in a ketone has more negative charge than the oxygen atom in the aldehyde. This oxygen in the ketone here has more negative charge than the one in the aldehyde. And this makes the carbon oxygen bond in the ketone to be more polar than the one in the aldehyde. The dipole moment of the aldehyde the dipole moment of the aldehyde is 2.5 D, and that of ketone is 2.9. For these reasons, we can now say aldehydes, they have a higher intermolecular forces. Aldehydes have higher intermolecular forces, and therefore they are higher. They have higher boiling points and melting points than their aldehydes of similar molecular mass. So you should better understand this. The electron donating effect of the alkyl groups on the ketone is the one influencing this. There are two electron donating groups on the ketone. For that reason, it makes for that reason it makes the oxygen on the ketone having more negative charge than the oxygen in the aldehyde. And for that reason, the carbon oxygen group in the ketone is more polar than the carbon oxygen group in the aldehyde. For that reason, the ketones, they have higher intermolecular forces than the aldehyde. And finally, for that reason, they have higher melting point and the boiling point than than the aldehyde of similar molecular mass. You will see that electron donating effect has a very big role to play in the property of aldehydes and ketones. Then we can go to displayed and structural formulae of aldehydes and ketones. You know, we will be starting, excuse me, let's give examples of some displayed and structural formulae of aldehydes and ketone. We will be starting with, let me use ethanol. The displayed formula for ethanol is this one. We will have this. That is ethanol. That is ethanol. And its structural formula is, this is the displayed formula. This is displayed formula DF, displayed formula. That is the displayed formula. Then its structural formula will be 1, 2, 3. There are 3 carbons, CH3, CHO. That will be the structural formula, SF, the structural formula. Then we go to, let me say, butanol. Butanol is another example of an aldehyde. The displayed formula butanol, we have 4 carbon, 1, 1, 2, 3, 4. That is butanol. Now, this is the displayed formula. Displayed formula. Now, let's go to the structural formula. The structural formula will be CH3. Oh, sorry. CH3. CH2. CH2. CHO. And we this is the structural formula. Structural formula SF. And the name we call this butanol. Butanol. We go further to other structures. Let me give for ketone. We will start with butan-2-one. Butan-2-one or butanone. Systematic naming, butan-2-one. So we have 4 carbons. For the ketones, we will have 1, there are 4 carbons. Butan-2-one, the second carbon. Then we fill in our hydrogens. This is the displayed formula, DF. Displayed formula. And the name of this compound is this is a ketone. Carbon 1, carbon 2, carbon 3, carbon 4. And now we can now say it is butan butan 2. Ketones are named with "one" at the end. Butan-2-one. The carbon chain are 4. We use butane. Now it is butan. Then followed by the position of the carbonyl group. The carbonyl group is on the second carbon. We now say it is butan-2-one. Now, and the structural formula for this would be CH3 CO CH2 and CH3. This is SF, structural formula. Oh, I did not give name for this one here. Okay. Now another example for this of a ketone. Another example of a ketone is pentanthreone. Pentanthreone will definitely be 5 carbon atoms. Pentanthreone, we have pent, has to do with 5. We will have 1, 2, 3, 4, 5. Pentanthreone. The carbon atoms are numbered in this way. From this end, or from this end, this is 3. This is 1, this is 2, and this is 3. So now, we now take this to be our position of oxygen. So now, this is pentanthreone. So that is 1, 2, 3, 4, 5. Okay, now let's fill the rest of the hydrogens. We will have 1 hydrogen, we cannot add hydrogen on this carbon here again because carbon forms 4 bonds, making a total of 8 electrons in the outermost shell. So we already have 2 bonds here plus these other bonds, making a total of 4 bonds. So we cannot add another bond here again. So now, what is the structural formula of this compound? The structural formula of this compound is CH3 CH2 CO CH2 and CH3. Let's name our compound. This is the structural formula SF. This is the displayed formula DF. And the name of this compound is 1, 2, 3, 4, 5. Pentanthreone. You must put a dash. The positioning of the oxygen, the third position is 3. Then ketones, they end in -one. The names of ketone end with -one at the end. So now it should be pentanthreone. Well, this is the IUPAC system of nomenclature. Well, you can call it pentanone. It's okay. Pentanone is okay. First, but for systemic naming, using the IUPAC system of naming organic compounds, you have to name it as pentanthreone. Another example of an aldehyde is an example of an aldehyde here could be, let's give another example to be, for aldehydes, to be, let me say 2-methyl butanol. So it is 4 carbon, 1, 2, 3, 4. I said aldehydes, the carbonyl group is always at the end of the carbon chain. You have it there. It has at least 1 hydrogen. Okay. Now we said it is 2-methyl butanol. The position from here, from the functional group, we have 1, we have 2, we have 3. We have 3. In this case, using this naming system, what we are going to do is our oxygen will be here. Our oxygen will be at this position. So our oxygen will be at this position. I mean the methyl group. It's a displayed structure, please. Okay. Three, 4. Two-methyl butanol. That is 2-methyl butanol. Okay. The structural formula will be CH3 CH2 CH CH3 CHO. And we call this is the displayed formula. And this is the structural formula. And the naming is 1, 2, 2-methyl 1, 2, 3, 4 butanol. Butanol. 2-methyl butanol. So that is how you can name it. So now, these are the examples of displayed and structural formulae of aldehydes and ketones. We started with ethanol. You have the displayed formula and the structural formula to butanol. the displayed formula and the structural formula. We went again to ketones. The first one is butan 2-one. You have the structural formula and the displayed formula. Then pentan 3-one. You have the displayed formula and the structural formula. So now we went last. The last one was 2-methyl butanol. You have the structural formula and the displayed formula. So I said aldehydes are named using the suffix "al" and the ketones with the suffix "on," following the same convention used in naming alkanes. But usually there is a number before the "on." There is a number before the "on." The IUPAC Convention, the International Union of Physical and Applied Chemistry Convention, in naming alkanes is the same way. But ketones, they are named with the suffix "on." Meanwhile, the aldehydes are named with the suffix "al." That is the only way you can name them. So a recap of our lesson today. Carbonyl compounds. I said carbonyl compounds. A carbonyl compound, this functional group is found in aldehydes, ketones, and the carboxylic acid. In a carbonyl functional group, the carbon is double bonded to the oxygen atom. And we went further to look at the properties of the of aldehydes and ketones as some compounds of the carbonyl group. I told you that the carbon atom, the carbon-oxygen bond is really polar. The polarity there is as a result of the difference in electronegativity. Oxygen carries a partial negative charge and the carbon carries a partial positive charge. Now, I went further in their solubility. The polarity in the carbon-oxygen bond influences the some properties in compounds having this group. An example is the solubility of these compounds in water. These compounds, the aldehydes and the ketones, are very soluble in water because they can form intermolecular hydrogen bonds with water molecule. You can see it from the structure here, how the lone pair of electron on the oxygen is used in forming a hydrogen bond with a hydrogen atom on the water molecule. So again, despite the fact that they are soluble in water, I say that their solubility again will also decrease as the molecule become larger and larger in size. The solubility also decrease because of the interference of the hydrogen bonds or the tails of the aldehydes and the ketones molecule. Then secondly, there is a decrease in the solubility as the molecule become larger and larger because as the number of carbon chains are increasing, van der Waals forces predominate. There are van der Waals forces that are now in control, no more hydrogen bonds. So now it took us to how, even though ketones and aldehydes of the same number of carbon atoms, they may have the same molecular formula, but there are still some physical properties that make them different. We're given an example of the boiling point and melting points, that the electron donating effect of the alkyl groups on the ketone and of the aldehyde make this property very visible. In ketones, the electron donating effect of the alkyl groups there, as they donate electron on the central carbon, or the carbonyl carbon, what happens? The electrons are being taken away by the oxygen. And that makes oxygen of the ketone having more negative charge than the oxygen of the aldehyde. In other words, we are now saying that the carbon-oxygen bond in ketone is more polar than the carbon-oxygen bond in aldehydes. For that reason, aldehydes of the same molecular mass with ketone, or ketones and aldehydes of the same molecular mass have different boiling points and melting points. Aldehydes of the same molecular mass, the ketone of the same molecular mass, will have a higher boiling point or melting point than the corresponding aldehyde. I say a ketone of the same molecular mass with the aldehyde will have a higher melting point or boiling point than its corresponding aldehyde, because this electron donating effect makes the ketone more polar, the carbon-oxygen bond in ketone more polar than in the aldehyde. For that reason, the intermolecular forces in ketone are higher than that in aldehyde, and that gives the ketone higher melting point, higher boiling point than its corresponding aldehyde. We're giving an example of propanol and propanone. Propanol and propanone. Now, finally, it took us to the different displayed and structural formulae of aldehydes and ketones. So you could see aldehyde, as we said, we gave example of ethanol, given their structural formula and their displayed formula. We also gave an example of butanol, structural formula and the displayed formula. Example of butan 2-one, structural formula and the displayed formula. Pentan 3-one, the displayed formula and the structural formula. So this is what we have covered today. In our next video on aldehydes, we are going to be discussing preparation of aldehydes and ketone in our next video through oxidation and other nucleophilic addition reaction. Learners, if you have not subscribed to our video, please subscribe to our channel and hit the notification bell. Thank you very much for watching.